Hi, everyone. Thanks for joining us today. We've got Bjorn Badsen here, and he's going to talk about his project Tablite. It's an open source project, and Bjorn actually posted this on the forum a while back, and we were quite excited about this project. So we wanted to help him get in front of the community and share this webinar with you so that you could learn more about the project. Thank you.
Thanks for the introduction, Lori. Yes, as it was said, the project is called Tablite. There is nothing really deep and meaningful behind the name, except that we had a guy on the team who always said things would be awesome if it worked like SQLite, but just was, great for what we needed it to. As he kept going on this tune over and over again, we just went like, all right, fine, we just call it Tablite because it works with table and it will keep him quiet. So that was kind of the opening for it. Tablite itself, I think I'll just go through the agenda, being that a quick introduction to what Tablite actually is, how you use it, and then onto some slightly more HDF-oriented deep dive on how it works internally. And then I want to go through what you can say in summary it's made for, and then we can take the Q&A at the end, where we will turn the recording off, so nobody needs to be afraid of asking any questions. Without further ado, the Tablite, as I'm talking about it, is the Tablite on Python's package index. And you'll see a newer version than the one you see here, because we are quite quick at adding new features. All the code is on GitHub, so you can just go there if you want to look around in the details. But that aside, there are no proprietary elements. Thematic I work for, they believe that it's a good idea to build open source libraries because it helps everybody to benefit and increase productivity, unless it's something that of course is some core intellectual property. And we've already had help from several organizations in building this project, but I will get briefly into that later on. Tablite is for tables what SQLite is for SQL. It's a library that helps us handle tabular data, when I mean processing and working with tabular data, I mean that we can take a data set of one kind that's somewhat similar to another kind. We can append them. If we want to, we can go and make joins between two data sets. We can go in and we can filter out according to our needs. We can do lookups between tables, pivot tables, so aggregation and rearranging the data. We can do groupings or group by summaries. We can do sortation and, of course, manipulate data types and select the columns that we want, plus whatever custom operations you might figure out or you want to plot it and chart it. So Tablite is made for this kind of activities here. And the whole goal is with Tablite is that you could do incremental data analysis. You don't need to worry about multiprocessing. It has to have a simple syntax to work with. It supports the idea that when you're working with Python on simple mathematics, you don't need to worry about data types. You don't want to worry about whether it's a float or an integer. You just want to do the math to make the numbers add up. A very important design goal in this list is the 1 terabyte data map, which we're pursuing that you can actually work in a tolerable way with over 1 terabyte of data on your local machine if you just have a solid state disk. And then finally, you don't waste CPU cycles on copying data when there is no entropy coming from that copy. I mean, if you change data, if you're doing something else with it, fine. But otherwise, no entropy should mean no copying. When I talk about a data map, an incremental data analysis, I would like to put it in contrast of this is kind of a typical workflow that some of our users work with, right? They do some checks on the data, various places on this gigantic tree, and they come up with an analysis at the bottom, which would come out as saying, here's one conclusion, this is what we're going to do with the data. And everything in between are steps that need to process all of these rows of data. And a typical use case here is 43 million rows with about 12 columns. and containing both date time into the Booleans, float strings, and nonce. It's messy data. Sometimes we see strings and integers or concatenated CSVs that weren't exported from the same system, though they had the same headers. But all in all, this data map here contains approximately 228 operations. And if you go in with a tool like an in-memory tool, like, for example, pandas or some other tabular data tool, then every time you go a step down this tree, you typically make a copy of the data so you can audit what has happened, and then you do some updates to it. Or you execute it all according to some script, and then when you add another step to it, you execute everything above. And that has a dire consequence, which is easily described here, that if you take those 43 million rows and you need to, just roughly handle 50% of the data or 228 times in a row, you're practically processing 5 billion rows out of your original data set. And that, of course, starts then to become slow to work with. However, if you can go in with your data set when you work with it and you process one step, and then it just stays nice and happily in HDF5 storage. And then it sits there. And then you go in and process it again. And you only take the changes that came out of that next process step and you store that. You don't worry about the rest, because the rest you have paginated or you keep it as a patch, right? Then the whole stack of patches, all the unique entropy that is in this data map, boils down to about 117% of those 14 million rows. So if you take that step-by-step incremental approach where you keep your mid calculations in memory, or you keep them locally available, right? Then you're just doing 51 million rows. And this is just, as a test case on this data set. So a data map is very important for us for incremental data analysis, and HDF5 has been a massive game changer by using that instead of trying to stay in memory or shared architectures. So now you know what we kind of made it for. Now I'll just go through some of the elements of the things we thought about while making it. The first of all is the task graph that Dask came up with, where they pull in some data, they distribute it out, they distribute tasks which contain the instruction set on what needs to be done with the data, and then they go in and do processing steps, and then at the end they aggregate it up or something like that. And again, this is a nice way of putting out a lot of work, like you might need to do in a join or in a lookup, or you're doing some other calculations and running it parallel. But when it comes for most of the data that you need to work with, if you're just doing a task graph and you keep increasing your amount of tasks, when you have all of these operations stacking up, this task graph starts to become really, really comprehensive. And if you go back to a reset state every time, just your data source and recalculate every time again, then you have this constantly growing compute time, which just becomes intolerable for the last few steps. So again, we keep the temporary calculations. Another place where we found inspiration was from Pony, which is an object relational mapper, which goes in and takes simple examples where you have something that looks like a generator expression or list comprehension, and then translates that into optimized SQL. And we really like that, but we can't use a database for what we're doing, because when databases typically establish relationships between tables, then all these referential checks, they tend to slow everything terribly down. And this is, again, one of the reasons why we said for keeping track of your transactions, there's nothing better in the world than a database. But if you need to do incremental analytics, forget the relationship. Just go for the raw data and go for your horsepower that you get from HDF5. We also saw some syntax, and here's a nice little post from LinkedIn, where a chap, he posted this and said, this is the R bit, and this is written in pandas. And I think I don't even know how to compare these two codes. The R1's entry barrier is to speak some English, while Python looks like it needs a 5-year degree in computer science to understand the code. And in all fairness, if you look at this one here, I certainly do not want to go in and pick this up from a colleague and debug this. I have an aggregation function, some wrapped inside a pivot data frame that I'm doing a T on. And then after I've done the T, I merge it on dates and fill some NAs. This is just painful to read. So we wanted to make sure that even though this can be flattened, we shouldn't develop a habit of writing this type of ... codes, even though some people find it really cool and really impressive because everybody then comes and asks them afterwards. So Tablite, we saw, let's do this just in the procedural way, where you go in, you import the data, you create, some joined fields, you slam in the blanks, you sort it, you do a pivot, you get rid of any columns you don't need. You might sort it again, and then you're done with it. That was just straightforward linear. And if you look at the number of characters you need to actually do this, it's marginally longer than one of these ultra compressed expressions. I actually think that the only difference here, when you really look about it, is the thing before the equal sign. That kind of just adds to it, right? So in this way, this is just an easier way to look at the code. Another element that we saw that the users kind of got shocked about sometimes, because we have a lot of people who are picking up Python from Jupyter notebooks and they don't come with a computer science degree or software engineering degree. They're a bit surprised that they suddenly need to worry about different data types when they're working with NumPy or HDF5. So we said, okay, fine, we'll take care of that. Don't worry about it. So all of these things here are just stick with native Python types. Is it a number? We deal with it. If it's a string, we deal with it. If it's a none or not a number, we deal with that too. So all in all, this kind of summarizes the whole essence of what Tablite is and what it can do for you. It's simple expressions. It's like NumPy and HDF in its processing power, but without types. And in many ways like pandas, but very much procedural. And then the most important thing is with HDF5, it is supported by the solid state disk on your computer or your server you're working on. You don't need a gigantic amount of memory. We've also worried about with the multiprocessing side of it. So how do you get Tablite? Well, you pip install it and you're done. And then you can just go to the front page where there's kind of a summary of all the functionality that we help with. You can loop over rows, over columns, you can slice, you can get columns by name using simple dictionary type operation. You can also get rows in the same way by just getting a particular number, a single row in. And if you want to update value, it's like saying I want to update index number 2 in my column A. So it's a bit like a dictionary with a list behind it. Very simple. If you need to update a lot of values, you just do a list comprehension, and Tablite takes care of the data structures behind. And in the same way, we can go into joins, where we have join types, left and right keys. We've got lookups. We've got the group bys, being you group by some key up front. You say what function you want to group by count and on which column, and then it spits out the data as you want it. I'll demo all of this in a tutorial, but right now I just wanted to kind of give you a quick overview of all of this. So in many ways, Tablite covers pretty much all the analysis functions that you could think of. I did a comparison with pandas, and we've got, I think, 107, 105% coverage relative to pandas. So who has more features? So on 22.11, which is a couple of weeks from coming out, we have all the parts, including copy to and from pandas data frames, if that's what you're more comfortable with. But for example, you don't want your data just doesn't fit in memory. So we can use Tablite to store all this stuff on disk, terabytes of data, and then you can work through chunks with pandas if that's what you are working rapidly with, and that's easy for you. So I am just going to take this one here, and you should be able to see my little notebook. Can you please confirm that I'm sharing the notebook? Yeah, we have heads. Yep. We have heads nodding. That's a good start. So let me just clear the output of all the cells. So very short. This is a tutorial that already sits at the bottom of the GitHub page. It's accessible to you. There's nothing special. I'll just go through some quick examples. So actually, the reason why I wanted just to run all of these was I wanted to show you a very simple thing. This is my temp dia, where I have Tablite sitting around, and you can see it's running the whole tutorial right now from front to rear. And Tablite here sits, and it's building up a number of megabytes of data because there's a lot of unique stuff in there. So in this way, Tablite, as you can see it here, is very quickly to load all the data in and work through the whole tutorial. And if I go in now and I just reset the storage, which you can see is about 1.1 gigabytes, you'll see that that clears out very quickly. Yeah, so that's the first thing. So table.reset storage just dumps all the data that you might sit around with and make your life easier. Now I'm just going to clear the rest of it. We already ran this fellow here. And to create a table is from Tablite import table. Pretty straightforward. You create a table like you would create a dictionary, and then you say there's a key, which is a column name, and then you have your values, and in they go. And there's nothing more to it. And if you want to see it and you're working in a notebook, then you can just do just call T for the table, which was the name, and it will render a nice little HTML style for you. If you're working in the terminal, you can get it out in ASCII art in the most beautiful style. For those of us who grew up with MS-DOS, we appreciate this. And if you want to see, some other elements of the table, you just want to inspect its dimensions, the string is there for you. One thing you can do with tables, if you don't have all the data available, like we have here, column by column, is that you can go in and add rows. That's supported as well. We go in and add columns A and B, and then we add them as a tuple at a time. And you can then see that these two tables are identical. So nothing special. If you want to import files, we have a massive menu for all the hints that there are for importing files. And in general, I would say it covers all of our practical use cases for the business. There's importing Excels, PDFs, the whole shebang. And it's quite quick in using, reading CSV files in using multiprocessing and then getting on with it. What makes Tablite very friendly in this regard is when you import a file, the first thing it does is it looks at how much free memory you have virtually on your computer. And then it says, how many compute cores do you have? And then it chunks this in little chunks in. And then the next thing it does is it generates chunks from that one file in a single streaming operations. So let's say I get 30 little chunks out, or whatever it might be. And then those individual chunks, they are then being processed column by column. So if I have equivalently, I've split my table, which might contain, millions of lines, and I've split that into chunks that says this can fit into memory, and that might be, 10 or 12 million lines. And then each CPU does a column on its own in its operation. And that means we are very rapid at spending the CPU intense time on identifying type, which you can see here from a CSV, which is just text, and then determining what to do with it. We also detect date and other date times and so on, all of that in Tablite using multiprocessing. So it will just eat your CSV. If you have non-ISO 8601 date formats, you might need to just modify your own the file importer, but they just sit in a dictionary, so you can just import them. If you want to select the limited amount of headers, or you don't know what's in the file because it's too big because you can't read it, then there is a friendly helper called get headers, and that just allows you then to swallow up the first 5 rows a bit like head and determine what the sample looks like, and then it gives you the ingestion of what sits there. So it tells you there's a delimiter, which is probably space here because it's invisible, and then you have the book itself with its rows. So in this way, we've tried to add some additional tools, and with 2211, there'll be a single from Tablite import tools, and then you have a whole catalog of them. So yeah, that's pretty much it. Aside from importing table, you can see you can just add columns whenever it suits you, or compute new columns. And then, as I mentioned, Tablite wants to make sure you don't have to worry about data types. So in this regard, for example, here I'm creating a new table with a column called mixed, and I'm putting in all kinds of junk, right? And the nice thing is what you put in is exactly what you get out. So it will tell you column name is mixed, and you have a row with mixed data types. And then inside, you will have all of those individual values, -1, 0, 1, some gigantic integer, all of these bits. What you put in is what you get back out again. Now I'll explain in a couple of seconds how this works. This is just a general kind of overview on a lot of these functions, and I think the only thing there is left to talk about is if you want to investigate which data types you're working with, you can go in and you can just call on the column, you can call the function .types. That will then give you like a histogram of the data types that sit in there. So a lot of people, they go like, first shot is, can I process this column with my function because I require 4 integers and a string for each row in this data. And then you can just say, yeah, if you got anything else but these data types in your column that you're looking for, you can raise a type error very quickly, right? So one of the things that, of course, follows on from this is if you got a column that came from CSV and that was really dirty, how could you then go in and see what data you got? And in here, for example, we have the benefit that we can just go in and guess data types. So if I'm just on this, if I'm just to the one above, if I go in and I have data types already loaded, but I pick data types and I want to do a guess, and I want to see that there is a bunch of strings in here, just to give you an idea of how it works. Then you'll see that it will just return integers instead, because it goes in and automatically recognizes what sits there. And I think if we do the same dates, I'm just hitting my keypad in the same random way. There should be no invalid dates here. It should go in and also just give you date times back, right? So it's very friendly in reading these things. So for importing data, that's nice. And then the rest of the tutorial, which goes through all of these details, is then on iteration, append, sort, filter, index, and all of these functions. So I could go in and dive into these. I think the thing that makes most of a difference to people is actually that you can just go in and define your functions, and then you can, construct a new table as it suits you. Here, for example, we want to just add 2 columns, and then we want to add some data to it. You're just computing on a slice that you've selected. And here I'm selecting a slice of columns. So I can just give me my selection of columns, and anything that comes in there as a string is just extracted and say, do I have a matching column? And then it creates a subtable with just that information. So in this way, you get exactly what you're pulling out. So there's more to it, but I don't think we will have the time to run through the details of all of the individual component in this tutorial for this. Yeah, there are many handful of helpers. So with that in mind, I think I'm just going to jump back to the agenda again for the rest of it, and then leave a little bit more to the Q&A. I mentioned that Tablite has multiple data types. So let's start with going through that and how it works internally. You've just seen this case where we put in all of those weird data types, and I think it deserves an explanation. It's very simple. Geert, he picked that from the HDF5 group. HDF group, he picked that out immediately by just looking at how it was organized. But I'm just going to go very detailed through this because I presume that the inner workings of how we use HDF5 for this is of interest. The first thing is we have the Python construct, which is a table, and a table has columns. No surprise, but the relationships are important here. Each of the columns, they have a page handler. The class is called pages, but it is a page handler. And the page handler has pages individually, and each of those pages, they're then of specific type. So when we go and put in just pure integers or floats, we come out with a simple type, which is NumPy native, it's HDF5 native. So quickly drop data in, get them out. Similarly, when we have strings and we're working with strings, we just do the text encoding, and we do the same for date times, time dates, and time deltas. So when you see this stuff here is saved in Tablite, it's actually sitting in there in UTF-8 encoding. We have the mixed page type, and that is the value itself as a string, because then what we put in, we're certain we get the same thing out, and there's a one-to-one relationship. And it will have a type code. So if I'm putting in an integer, I'll see that will be a type code 3, because it's a third in my hierarchy. And when I then load it back out from HDF5, I'm taking that string and giving it the function, and then I'm converting it back to an integer. And the same when I put it away. And then just for the pure habit of having the ability to work with enormous redundancy, we also have a sparse page type, which takes a default value, typically none. It determines that all by itself. And then it stores the value of a string, and then uses the sparse column constructor for a method for keeping track of the index. So that basically becomes a byte string, integer for the type code and an integer for the index. So in this way, we can keep track of all of these. And as you can see, this is a mixed column. So we use that one for just having a type code that then reflects all of it. And when you go into the heart of HDF5 and you really look at the details here, here I've created a table again with various columns with various data types. And I'm checking that I'm getting the right thing out again. So if I'm just looking at HDF5 from the top, right, I can see that there is a table class which doesn't really, contain any additional information. It contains some metadata. When I go in and look at my attrs on items, then I can see that I have a column A, which refers to column 14, and I have column named B, which is this one, and that refers to column 15 here in this case, and so on and so forth. And the numbers themselves, they're arbitrary, but the column names and the relationship to the table are, of course, very, very strict. So if I then go in and I inspect my columns and I look at what do they contain, I will see, for example, that column behind A14, that contains, it has a length 2, and it refers to my pages data set, which are my pages data group, which is page 1. And then if I go in and inspect all the pages again, I'll see there are numerous pages. Page 1 just has 1 reference point, where, for example, page 12 has 2. It has a reference to the data itself and the type codes that's associated with it. But if I go in and inspect page 1, here just go in the regular lookup method on H5, I can then go and see that it's a page which has an integer 32. Right now it's UTF-8 encoded. And it's a page of a symbol type. So when we load it out, we know what kind of type to load it as. And if I want to blurb out all of the data, I can just use the slice operator, of course, and then I get an array out with -1 and 1, which is exactly what we put away, and which is exactly what we're testing for when we get it back. Similarly, I can go in and inspect this one here, which I think is page 11 or whatever. And this you'll see in the same way, just walking the same stack backwards, is an empty string, and the UTF-8 encoding for 1000 as a string. And again, it came from a string type, and it was a page as a string type, and it used the IO type for storing it. So that's also very linear to look at. Page 12, which I mentioned earlier, had a type code with it as well. Comes up as a mixed type, and you can see it's 2 gigantic integers here from Python, which are stored as strings, byte strings, and you can see that they are under the page number 12 types. They include 2 type codes, which is 3 and 3. Yeah, so we know they're integers, despite them being very, very large integers. That normally an integer 64 system would say can't store that, overflow. And finally, of course, we have a list which contains a none and a 1. And here we have a sparse type because the default of none is a sparse value. And it will come up as a value with 1 that exists as a type 3 on index 1. And we can see that's correct because the index 0 is occupied by none. So in this way, we have then put all of this data away, and we used a simple hierarchy of storing tables, which has used their attributes to refer to you can see the columns as a dictionary, and then the columns itself, they refer to the pages, and then each of the pages themselves, they then contain the data. So very straightforward. For those who like more a graphical interpretation, this is like when we construct a page, we go in and quickly analyze what we're getting, and then we decide which of these data types we work with, and then we pop out with a page. And that's nice because this construct here means that when we go in and we have, for example, something that starts out as a pure column with integers, and we just dump them into an integer-friendly format, a simple page that doesn't have the type code, and we try to append or extend a string, then we will throw a type error, and then we'll just go and recast that particular page. Now, think about this. If I have a page size which contains 1 million values, right? And I'm rolling over and I'm saying I'm trying to insert maybe a text string 100 somewhere, right? Then I have to recast that page into the new type. But if my pages are individually not very large relative to the whole data set, which might be hundreds of gigabytes, right? Then I get the benefit that I only update a page. The other pages in that column might still be string types or might still be integer types. There's no conflict in that. So the trick here is minimizing the overhead of dealing with this work. So that gives us a very nice way in practice of coping with these cases where people update pages with a new type or new values without having to recast the whole column. I in particular like to throw in an example here where we have the type functions or the type codes, which pretty much covers everything you'd work with in Python, particularly because we also can take some arbitrary object. I threw in a quaternion because a complex number wasn't enough for me. So I take this and I construct it down here. And in my quaternion, which is shown with the number of values, I put it into a table. And at that point in time, it just gets stored as a pickled object. And when I call it back out again to say, give me a list of the values inside this table, then I get my quaternion out again. Zoom. And you can see that that quaternion is exactly the same as the other one. So this kind of explains the whole type system around how we give the convenience to the user of not having to worry about types at all in Python. So one of the questions that I often get on top of this is if we can store all of this data here, how come that it's so easy to use Tablite in terms of memory? How can it be that it doesn't consume more in RAM? And the answer here is Tablite's on disk. The data's on disk, right? It's only the metadata we keep in memory. And I have this little example here where we have it's in the Jupyter notebook as well, where we go in and create a little table with method, memory, and time. And then we go in and we look at 1 million records. And we then create a couple of test tables. So we use psutil to figure out how much memory we are consuming. So on the first round here, I take the classical column format. And this here goes in and stores the number 11 for each of 10 columns. And then we repeat that 1 million times. So we have a column with 10 values and we have 1 million of them. And that then gives us an entry in our little table with the memory footprint. And then we do the same for the columnar format where we have 1 million values and then we have 10 columns next to each other and we measure the memory footprint. And just for the fun of it, we look at an array as well for integers, well knowing that it's a very limited test case. And then finally, we use Tablite tables where we go in and we create 10 columns, all of them with 1 million records in it, and look at how much memory that consumes. And then the magic trick at the end is I do a copy of that table and show you how much memory we then still use. So it comes out as this, where we have 1 million lists with 10 integers. That will use about 138 megabytes of RAM in Python. And if I go in and work instead with 10 lists which each contains 1 million integers, then we save the overhead from managing all of those lists. So we drop down to 82 megabytes of RAM. And if I do the same in array, we can see there's some management we save as well, which is we could get down to 41 megabytes of RAM with arrays, well knowing that we can't handle nonce and we can't handle, you know, oddities that follows with it. And then the digit 11 is a really friendly case here, but it, you know, sets a kind of a low amount of problems we could face. And then we use Tablite with 10 columns, again, with 1 million integers in it each, and we drop down to 2 megabytes. And when I copy this table here, Python doesn't seem to notice it. It might just because it still reserved the cache on the, it still reserved something for the garbage collector and then just refreshes it before we can measure it. But in all, I mean, we're clearing out, we're using garbage collector. We're clearing out the memory after each of these tests. We give garbage collector time to collect it, you know. So the measurement, as far as I could figure it out, is real. And we go from 138 megabytes down to 2 megabytes, including the imports. So all in all, you know, it's not that much extra in time, and yet it's super efficient for the way we can work with memory. Simply, you know, standing on the shoulders of HDF5 to do all the data management. And as our research has shown, when you're doing incremental analysis, you don't need to have all the data in memory. You just need the last state that you then want to work onwards from. And yeah, that's it. We've got a test which I put on the forum, which shows 9 billion records, which is constructed by having 8 million records bottom to bottom. This is typically a test case with, you know, various floats, mixed codes from an industry partner. This is all synthetic data, but we use it for tests. And it's pretty representative, you know, with date times and temperatures and whatever comes to it. But what's nice to see here is that doing the slice of both the head and the tail can happen in 0.7 seconds. And that just won't be possible. I mean, if you have a row-oriented format, yes, you can go in and read the first rows and the last rows and get it out really quickly. But you still need, if you have any encoding around, you still need to go around that whole data stream. But because we've used HDF5 to store pages, and we can almost at constant time access those pages, on this massive data set, we only need to read the first page, which is just a bunch of numbers here. Just a bunch of numbers here, integers here, a couple of date times, some integers, and a couple of strings. So we just read out the first page of this block and the last page. And as long as our ability to go in and search for a slice is effective and clever enough, then that takes no time. And we have a very simple way to do that. So that means that, you know, if you need to go in and get a particular slice of a data set and you work with that, whether it's by column or it's by rows, you get the best of both worlds. You don't care about that anymore. So yeah, it means that sloppy code can actually be fast. So good. Since I'm talking about speed, I think the next element is, yeah, the way we work through this data, just as I showed you, was we make the CSV with a dummy synthetic data set, which is this one. And then we go in and we start the timings and we import the file. And then we took the data set. This is from the test case. We import the file again, which should show that it has already seen the config with the path and all the details in it. So it's not going to spend any time on importing it twice because we already have it. And we don't change data that already sits in HDF5 that already exists. So if it's the same source twice, don't bother, don't touch it. So that will be very quickly when it comes out. It's a couple of milliseconds, but it's important for us that we detect repeated loads of the same data set because it's just pointless CPU work. And then, of course, finally, we go in and just take and say, we calculate the repetitions. I think it's some was that 40,000 times of that table that we have, and then we do the time measurement on that table, and that's how we get to the numbers that you saw here. So in this way, and it's a real test, right? Because whether we read across the slices or we read the same slice many times, technically seen, it's just about hitting the right index in the HDF5 storage. Multiprocessing itself here is at use, and here's an example with a left join where we go in and we analyze the left and right table here, and we just create an index, and then we go in and we create a shared memory array for left and right index. And as you remember, when we work multiprocessing, we work on a page and we work on a column at a time. So if I need to look up a page, on a page in the data set, and I need to reorganize this according to some sortation, then this algorithm here is technically seen optimal because it goes in for all the left columns. It goes in and does uses that indexing task, and it does the same for the right columns. And then we just systematically construct the joint table from left to right, page by page, and then process it in chunks. And that's what then happens after we've created the tasks. The task manager comes in and then it executes all of the individual tasks. And once it's done that, then all we do is we go and grab the table ID that has been created, and then we load all of those individual columns and just associate them reversely with the table. And then we can kill the memory footprint from the shared index, and then load the table and give it to the user. And each of these indexing tasks are super simple. It just took some time to get to the root of it. But what really happens is for each of the virtual CPUs on your machine, it goes and fetches the data of a block size that fits in memory. And then it just reads the data as it sits according to the sorted index for that slice. And then once it's constructed that new little list of values, again, each page, each column, it closes its connection to that shared memory array, and it just writes it out, and boom, done in no time. So those are kind of just some elements, and where we really see that going in and maintaining this hierarchy, that a table has columns, that has a page handler, and then we have individual pages which are up to about 1 million entries per row or per page. That seems to work really, really well. If we go smaller pages, we tend to get more IOPS, which is not beneficial. If we get longer pages, then we get a lot of replacements, which isn't necessarily ideal either. So I think in some way we've hit like a nice size around that 1 million entries for the data sets we work with. But should you come across something that's kind of like I'm getting bad performance, please just post it on the GitHub under issues, and we'll get some of the astrophysicists to look at it. So yeah. All right, so that was speed talking about how HDF5 works internally. The next thing I'd like to look at is just summarize what it's made for, and then we go to the Q&A. So in summary, ETL, dealing with messy data because we can handle multiple data types. Data pipeline preparation, so you're staging data, you're importing from various formats, and data cleaning, all of those things that contribute to incremental analytics. We definitely see a benefit that you avoid the replication of data because we have pages, and again, if there's no entropy, we don't store it. We can store slices, we can manage all of that in memory. We only manipulate metadata. There is a nice handful of helpful functions, and the more people who ask me if it can do this or that, either turns out to a little cookbook recipe or it becomes a new function. Data imputation is the hot thing at the moment. A lot of people are struggling with figuring out the best method for doing that. We've got the recipes, I just need to port them. Another thing is, as a user, you do not need to worry about RAM or CPUs because all of the embedded functions, they peg the memory footprint that you have free and just crunch the data. So that's nice. And then finally, of course, the style of coding, if you just work incrementally, it's pretty easy to audit. You don't need to wonder about some archaic syntax and figure out how it works. So far, I've seen a number of users and a number of companies where we know they're used in production. How experimental that is, I don't know, but at least we have some early adopters, which is always promising. Some of the feedback that the users gave to me that I was allowed to put in was, first of all, if some of them get an ERP system dump, normally it could take like 5 days, a little more than a week to clean that up, depending on how messy it is and how many migrations the data provider had been through. But right now with Tablite, it's kind of a thing you can do same day. You don't need to do reruns of your data as you get deeper and deeper in the stack. You just do one step and then the rest sits on disk, and then you work incrementally with the next one. And if something went wrong, you go a couple of steps back, you update and just cascade it forward. Nice and easy. It's less code to cope with edge cases, which are commonly known for dirty data. And this is particularly around the types, where dealing with dirty data, offset columns, and all of this is difficult. Tablite has a function that's called stack, which goes in and takes two tables. And if they have almost the same columns, it will match the ones that match by name. And then it will plug in nones for the ones where it doesn't match. And then you can just stack them all. The order of columns doesn't matter because Tablite sorts that out itself. Users also tell me that, of course, it's a little bit slower than NumPy because broadcasting is not implemented. But because of all the other things, it's actually faster to use than just working with NumPy in isolation, because you get the whole benefit that you don't need to worry about multiprocessing, running out of RAM, etc. So that's one of it. And one I get some praise for is a function called datatypes.guess. That seems to make many headaches go away because it comes up with a very reasonable guess at the end of the day. So yeah. All right, that's kind of the whole run for Tablite. I feel like I've been speed talking. I think it's time for the Q&A. I'll leave this one here sitting on for the Q&A, and I think Laurie wants to stop the recording. And then you can ask me all the questions that I hope I won't be giving too embarrassing answers for. So thanks for listening.